In this video, we're going to take the additive principle up to a new level and look at the principle of inclusion-exclusion. And the book calls this PI as an abbreviation there. So we're going to introduce a problem of counting objects in the union of two sets where we do have elements in common. We're going to generalize this reasoning to get what's called the principle of inclusion and exclusion for two sets. Then we're going to set up the reasoning for principle of inclusion and exclusion for three sets, and then you're going to work that part out in your in-class activities. And then finally, we're going to do an example. So here's a problem to sort of get you started. Let's say JoJo makes a grocery list, and then JoJo's roommate Joanne gives them a grocery list of her own. JoJo's list has 13 items. Joanne's has 15 items, but they made their lists independently, so they actually got 7 items that were on both lists. Question is, how many items will JoJo get from the store, from the combined lists? So let's use a Venn diagram to kind of figure things out. So here's a circle indicating JoJo's list. Here's one indicating Joanne's list, and then of course the region in the middle is the items that are on both lists. So where do we start? Well, one place to start is let's figure out how many items are in each region of the Venn diagram. One of those regions we can figure out right away. That's in the middle. There are 7 items that are on both lists. That center region has 7 items in it. Now, once we have that, we can now finish out the rest of JoJo's list, right? We already have 7 items of JoJo's list accounted for. There are 13 items altogether. That means there are 6 items in this region to the left. That is the list of things that are on JoJo's list, but not on Joanne's list. And we can do the same thing with Joanne's list. We have 7 of her items accounted for as well. She has 15 items altogether, which means that the items that are on Joanne's list, but not on JoJo's list, that's 8 items. So now we have all 3 of the regions figured out. And to figure out how many there are altogether, we can just add those things up. 6 plus 7 plus 8 gives us 21. So that's one way of solving the problem. Completely reasonable way of doing it, but there's another way as well. Here's our alternate method, and what we're going to do is kind of very generally kind of a technique that we're going to see repeated in different ways, but it definitely repeated in different counting methods that we use throughout this chapter. We're first going to make a guess at what the answer is, a reasonable guess, not completely out there. And then we're going to make some adjustments so we can get the exact answer. So JoJo's list has 13 items, Joanne's list has 15 items. If we want to just make a kind of a wild guess at the answer that we don't think is right, but at least, it seems reasonable to start out with, it makes sense to add those 13 and 15 together to get 28 items. Right? I mean, that's what we did back when we were using the additive principle. And so it seems like a good place to start here. Now, of course, this isn't going to work because some of the items get counted more than once. In particular, there are items that are common to both lists that get counted more than once in that accounting. So why don't we see if we can figure out how many times each item gets counted. And once again, we are going to use a Venn diagram to help us figure that out. So when we count JoJo's 13 items, each item in JoJo's list gets counted once. So here's JoJo and Joanne, our Venn diagram. And so after counting JoJo's items, we get all these items in here get counted once. All these items in here get counted once. At this point, right, we haven't counted Joanne's items yet. Once we do that, that may change. So now we're going to add Joanne's 15 items. Now, each item that's only in Joanne's list and not in JoJo's list, that also gets counted once. However, all the items that are in both lists get counted again. They got counted once when we counted them in JoJo's list. They get counted again when we count them in Joanne's list. And so that means that region, the items on both lists, that's 7 items, get counted again. So we get a nice little 2 in there. So after we've done that 15 plus 13, what we've done is we've counted all the items once except for the items that are on both lists. So now we can start making adjustments, right? So, and to do that, all we have to do is subtract the number of items counted twice, right? Because what happened to those items? We counted them once, that's great. We counted them again, and now we're just going to subtract the number that we counted too many times. So our total number of items, we get 15 plus 13. We counted 7 items twice. We subtract that 7 so that they're only counted once. And that gives us, well, 21. Same answer as before. So as in general, our principle of inclusion-exclusion is going to go like this. Suppose we have two sets A and B. The question is, how many elements are in the set A union B? Remember, those vertical lines indicate cardinality, which is the number of elements in the set. Our guess, of course, is going to be the cardinality of A plus the cardinality of B. We just take the number of elements in each set, add them up, just like we did with the 15 plus 13 in the previous problem. But of course, not all the elements are going to get counted once. Some are going to get counted more. And if we figure out how many times each one gets counted, well, after we count the elements in A, those two regions get counted once. Once we count the elements of B, well, the items on the very right get counted once, but the items that are common to A and B get counted twice. Once again, since the items in A intersect B get counted twice, we need to subtract those from the total to get them so they're all counted once. So our cardinality of A union B is going to be the cardinality of A plus the cardinality of B minus the cardinality of the number of elements that we get counted twice. That's A intersect B, and that gives us our total. So as an example, if you are in a room of people who either like strawberries or blueberries or both, there are 12 people who like strawberries, 10 people who like blueberries, and 5 people who like both. How many people are in the room? So if we let S be the set of people who like strawberries, B is the set of people who like blueberries, we are looking for the cardinality of S union B, right? All the people, strawberry and blueberry people get put together. That's what we want to count. Well, we can use the principle of inclusion-exclusion. The cardinality of S union B is equal to the cardinality of S plus the cardinality of B minus the cardinality of S intersect B. Well, we know that 12 people like strawberries, 10 people like blueberries, 5 people like both, so we plug those in, and that gives us 17 people. So now the question, we figured out how to count the elements in 2 sets, even if they have some intersection. How do we do it for 3 sets? Well, as I mentioned before, you are going to be doing that on the activities in class. Keep in mind, though, the same general principles apply. You're going to count recklessly, like we did before. You're going to figure out how many times each one gets counted, which is going to be a little bit more complicated because we have 6 sets and therefore more regions that we have to worry about. But then what you do is you make adjustments so that in the end, everything is counted once. Anyway, go ahead and take off and do that with the principle of inclusion-exclusion. That's the name of the PDF file included with this video.